Take one.
So, welcome everyone to the second trimester of Bhaskara Pratishthan on triangle groups, Bell uniformization and modularity. It's a great pleasure today to have with us Professor Shaunak Dev from IISc Bangalore. And we'll be speaking on the second trimester. Welcome everyone to the second trimester of Bhaskara Pratishthan. Oh, I think there is some echo. Is it all right? Okay, so maybe I can start again. So, yeah, welcome to the second trimester talks at Bhaskaracharya Pratishthan. Today's speaker is Professor Shaunak.
Sorry.
Shaunak,
Yes, true.
Is your other thing muted? Or?
I think it is muted.
Yeah.
Now go ahead. I think we have a problem at my end.
Okay. So yeah, so today's speaker is Professor Shaunak Dev, and he will talk about modular curves. This is the first talk on modular curves. So welcome, Shaunak, and please go ahead.
So thank you, Somnath, for introduction, and thank you for invitation to speak in this very nice program. I'll be talking about modular curves. Maybe I just write modular curves. So this is the first part.
Can you enlarge the screen a little bit?
I'm not sure. I think this is the largest screen, unfortunately. I'm not sure how to enlarge it.
You stretch by fingers? No problem.
Okay, yes, it is stretching. Is this okay?
Something is moving, but yeah, it's okay. Yeah, it is bigger.
Yeah, okay.
Font will come bigger. Okay, thanks.
Right. So the title of my talk is Modular Curves, Part 1. So there will be two talks in modular curves. In the first one, my aim is to sort of recall whatever you have seen in the program so far about modular curves, and talk about its modular space property a bit, and then go on to to state various versions of the modularity theorem, the celebrated modularity theorem. So the two parts of my talk, they're going to be mainly dealing with modularity theorem. I'm going to state various versions and try to give a connection between them. So since we have two talks, I guess I can go a bit slow and not be very hurried. And at the end of this talk, I can decide on what will I do in my next talk. Okay, so just a quick recall from Mihir's talk that he gave last semester. Okay, so the quick recall is that we let H be. So Mihir gave a talk on modular curves actually, and he talked about the Riemann surface structure on modular curve, and that being an algebraic curve. So just to set up a notation, H is the complex upper half plane, which means all complex numbers whose imaginary part is greater than 0. We know that SL to Z, it acts on the upper half plane, and it also acts on H union rationals. H union rationals, H union rationals union infinity. And we know the action is very easy, that if you have gamma is A, B, C, D, then gamma dot Z is AZ plus B upon CZ plus D. And you extend this action to rationals and infinity. So on infinity, this gamma dot Z will be just B by D. And on rationals, it will take it to rational unless the denominator vanishes, in which case, if denominator vanishes, it is taken to infinity. So that's how we have this action on upper half plane and also on this upper half plane union cusps. Okay, and if gamma is a congruent subgroup, of SL to Z, this means there exists an n greater than 0 integer such that gamma of n is inside gamma. So for some integer n greater than 0, gamma of n is inside gamma, and this is inside SL to Z. So gamma is a subgroup of SL to Z, which contains gamma of n for some n, and gamma is all the matrices in SL to Z, which reduce to identity modulo n. Okay, so whenever you have a subgroup which contains gamma of n for some n greater than 0, we call it a congruent subgroup. And we are interested in studying these quotients. So we are interested, we are interested in studying these quotients. So one quotient is y of gamma, which is just the upper half plane modulo the action of gamma. And then the other one is x of gamma, which is upper half plane union q union infinity modulo the action of gamma. Okay, so we are interested in studying these two quotients, and x of gamma is basically known as modular curve of level gamma. And even within this, the cases of particular interest are these two, maybe I can just write cases of specific interest.
Level n.
Of level 1 actually.
No.
Sorry, what?
It is
You
of
mean
level
level
1.
gamma?
No,
That is right. Gamma is right. Yes.
Gamma contains gamma n. It could be anything. So level 1 will be when gamma is all of SL to Z.
Yeah, okay, thanks.
So cases of specific interest are when this gamma is either gamma naught of n or gamma 1 of n. So gamma 1 of n is all matrices in SL to Z, which reduce to unipotent, upper triangular unipotent matrices, which means modulo n, it becomes 1 star 0 1, and gamma naught of n, these are all matrices in SL to Z. When you go modulo n, they become upper triangular, star star 0 star. Okay, so these two are our mainly like specific cases of interest. Even though we are in general interested in studying x of gamma for all congruent subgroups gamma, these two are special. Even within that, we would be like slightly biased towards studying these two cases. Okay, so the theorem that we so obviously you have an action of gamma on an upper half plane or the compactified upper half plane, and you're going modular group action. So you have a geometric object. And the theorem that we saw in Mihir's talk was that x of gamma is a compact Riemann surface. Okay, so this is the theorem that we saw, and sort of this Riemann surface structure is coming from the upper half plane itself. The upper half plane, you have the various neighborhoods of your points, and you're taking quotients of those neighborhoods. So you can use that to get this this Riemann surface structure on x of gamma. So x of gamma is compact, y of gamma is not compact. Y of gamma is also a Riemann
Points, right?
Sorry.
With some branch points.
Yes, but even with that, x of gamma is, I think, a compact Riemann surface, right? I mean, the statement holds, isn't it?
No, there are some branch points remain.
Even in x of gamma, I thought like for any gamma.
Yeah.
Okay.
For many cases, gamma 0n has some torsion elements.
Yes.
And so these torsions will create the branching.
Mm-hmm. But I thought you did prove that x of gamma is a compact Riemann surface, because that's how we see it as an algebraic.
As an algebraic curve, it is birational to a non-singular algebraic curve.
Algebraic curve, I see.
And non-singular algebraic curve is a compact Riemann surface.
Compact Riemann surface. Yeah.
Algebraic projective curve.
Right.
But that is birational, right?
Yeah, birational.
Birational. Okay, thanks for the clarification. Right, so some examples that, you saw in his talk were like x of 1, which is like P1 of C, and similarly x of 2, which was like P1 of C. I guess this is up to birational, I think, in light of the discussion that we had just now. But yeah, these both of them had the genus 0. And because we have this compact Riemann surface, the theorem was that there is an algebraic curve attached to it, again up to birational isomorphism. So theorem that because x of gamma is a compact Riemann surface, there exists a unique, smooth, irreducible projective curve C of gamma. I'm just denoting it by C, but this notation will not appear again, such that x of gamma is given by sort of the complex points of C. And thanks to this, because of this, we can think of, so we can also think of x of gamma as an algebraic curve, and which we also call a modular curve, which is also called a modular curve. Okay, so sometimes we'll be referring to the Riemann surface as modular curve, but sometimes we'll be referring to this x of gamma, the algebraic curve that is coming from this theorem, which is giving you an algebraic curve corresponding to compact Riemann surfaces. So we'll also be calling this algebraic curve as Riemann.
So you mean smooth means non-singular?
Yes, non-singular. Yes.
Then the statement is not correct.
I see, because of the
because of the branching.
Yeah. I see.
No, it's true.
And that branching is
compact Riemann surface can be identified as complex.
Singularities of cuspidal type.
May you want to say something?
Yeah, I'm saying it's true. Any compact Riemann surface is C points of some smooth algebraic irreducible.
Not biholomorphic. It's birational.
No, it's no. It's
No. Look your X1. It's not P1C biholomorphic.
X1 is P1C. X1 is P1C. It's not. It's
No, X1 is not P1C. It has two branch points of index 2 and 3. And
but still, the underlying complex manifold is
P1C. Yeah.
X1 is. I mean, it has additional structure as you are saying, but it's still P1C.
Exactly. Yeah. The underlying complex manifold is still P1C. Mir is correct.
You can say P1C with the decimal structure, no?
No, there are two branch points where the branching is index is 2 and 3.
But I mean, yeah, you are specifying these 2 points, but if you just forget those spatial points, then it's P1C, right?
In terms of hyperbolic geometry, the angle around a point of index 2 is only 180 degrees and not 360 degrees.
But that we don't need that to have this smooth projective curve, right? Any compact Riemann surface can be identified as complex points of smooth.
Yeah.
It is homeomorphic, but it's not biholomorphic because the singularities are of cusp type. And it's cuspidal in the sense of algebraic geometry. Cusp is a hyperbolic geometric notion. Cuspidal is a special type of singularity.
Okay. I don't get this.
Yeah, even I'm not. I thought like x of gamma is always a Riemann, even though you're right that there are these points, but that doesn't matter when you give it a Riemann surface structure, because those are just points with additional automorphism. You're just taking the orbit around that. You can always.
So it's interesting. X1 is not a quotient of the P1C by some finite group action. Locally it is, but not globally.
Not globally, yeah. Yeah, but I thought X1 is P1C, right? I mean, you can give it actual Riemann surface structure. I thought it was in Mihir's term.
Let us go ahead. Let's go ahead.
I think Professor Kulkarni want to say that there is a orbifold structure. It's not like as a manifold you can realize it as a P1C. There is an additional structure P1C with some additional structure because of these torsion points. X2 where it is a torsion free, and so it has a smooth manifold structure. It is like really a P1C. But X1 is not really a P1C. It is a P1C with additional structure.
I see.
Yeah,
Let me
but
say
the
it
theorem,
again. It is homeomorphic, but not even C1 isomorphic.
I see.
Not even C1 isomorphic. And certainly not biholomorphic.
Right. But I think if I understand correctly, this problem goes away whenever the torsion thing is taken out, right?
Yes. It as long as it is torsion free, there is no problem.
Yeah. So I think something like that.
If gamma is torsion free, there is no problem.
Gamma, or is its image in?
But gamma 0n many times has torsion.
Right. But do you need gamma to be torsion free, or its image in modulo scalars to be torsion free? I feel like you need its image modulo the scalars to be torsion free, because the scalars, I mean, -1.
Scalar is just plus minus identity.
Yes. So you want gamma to be torsion free modulo plus minus identity, right? Or not?
Yes.
Yeah. So, but gamma naught, I think, is torsion free modulo plus minus identity.
No, gamma naught n is not. Gamma n is.
No, gamma naught of n.
Gamma naught n not always, but it is also like n equal to 4, it will be a torsion free. So there are some examples. Yeah.
After, like, if your n is bigger, then it becomes torsion free modulo plus minus 1, right?
No, gamma naught.
It is not always. It is not always. Yeah.
No, I'm not saying it is always. I'm saying if n is greater than 4 or something, I think gamma naught.
Yeah, for higher values, yeah, it will be torsion free.
That's what I'm saying. I'm not saying for any n.
Or whenever gamma is torsion free, there is no problem. It can be realized.
Right. Precisely. So
when there are torsion point, then it is a problem, and that's what I think the point of Professor Kulkarni. Yeah.
Yes. I understand, and I think this you're right to point it out that it becomes, as you said, it becomes something like an orbifold. So in whatever I am saying, if you take your n to be high enough, most of the things are true. This does.
I'm saying that we don't need the orbifold structure to say that X1 is algebraic.
Algebraic is different.
Right.
Yeah, but that's what our discussion right now is.
As an algebraic variety, it may have singularities.
No, how can compact Riemann surfaces can have singularities? It's a smooth manifold, right? Even algebraic.
It's not a smooth manifold. It's homeomorphic, but not smooth. You get that cone point there.
Yes, that's right, Professor.
Yeah.
Okay, let's Shaunak go ahead and we can discuss all together.
Sure. Yeah. So just to clarify the confusion, there is some subtlety going on. You have to be very careful with the level. That is something I was anyway going to mention later on, that you have to be very careful with the level, because sometimes this moduli space structure, you may not always have a curve which sort of represents the moduli space. It could be stack or something. There are some things that needs to be taken care of. But if the level like n is say greater than 3 or 4, most of these problems go away, including these various torsion things and various things. Yeah, sorry for being a slightly sloppy initially, but I hope my point is getting through. Okay, so we have this x of gamma, and you can attach you can think of it as an algebraic curve, and it's obviously an algebraic curve over C, and then the question arises that can we define it over something smaller than C? I mean, C is too big for us, especially for number theorists. And the theorem is that the first theorem is that x of gamma is defined over a number field. Obviously, the number field will change if you change your gamma. Right. So So if you change your gamma, then this number field is going to change. But the moral of the story is that x of gamma has a model over a number field, and we are even lucky. Like if you go to x naught of n, which is x of gamma naught of n. This is the notation we'll be using, x naught of n. This is defined over Q. You can just use it as a. So this is something that is defined over Q. So it's a curve. It's an algebraic curve over Q. You can actually have a model over Q, or Z attached with 1 over n actually. So it's a very nice thing. You can reduce it modulo P and so on. Okay, so this was more or less like a recall of Mihir's talk, and now I would like to go to this moduli space interpretation. So if you look at the modular curve without these cusps, without Q and without infinity, then they can be thought of as like some moduli spaces, which are interpolating data, which consists of elliptic curves and some additional data related to them. So maybe I can write it down that we can think of y of gamma of n, y of gamma 1 of n, and y of gamma naught of n. So if you see now, what I'm doing here is that I'm taking the y part, which is just the upper half plane modulo the action of these groups, not upper half plane union cusps modulo this action, and these as certain moduli spaces of elliptic curves along with additional data. It will be clear just in a while what I mean by this. Additional data. So what I mean by this is that whenever you take a point of this sort of, it is sort of interpolating all elliptic curves over C, which along with some data, all these quotients. If you take a point, it will correspond to certain elliptic curves along with some data, some isomorphism class of this thing. That's why it is called moduli space. And just to give you an I will obviously state the exact theorem that I want to state, but just to give you an idea, what we do know is that if E is an elliptic curve over C, then there exists a lattice lambda, which is just Z linear combination of omega 1 plus omega 1 and omega 2. So this is a lattice inside C. So omega 1, omega 2 are linearly independent over R. Such that E is isomorphic to C modulo lambda as a complex Lie group. So in other words, every elliptic curve over C is basically just C modulo lattice. So this is a well-known theorem about elliptic curves over complex numbers. And what we can do is that we can have this normalization. We make normalization that this omega 1, the quotient omega 1 modulo over omega 2, it lies on the upper half plane. So whenever I write a lattice, whenever there is an elliptic curve, I say that there is a lattice lambda such that E is isomorphic to C mod lambda. And when I take the generators of the lattice, I will always use this normalization that if omega 1 and omega 2 are generators, then omega 1 over omega 2 is in the upper half plane. And we can always do this because if it is not true, you just replace omega 1 by minus of omega 1 and it is true. It is never going to be a real number because they are independent over R. Okay, so this is a sort of a well-known structure theorem, if you will. But now what is this telling us is that, suppose your lambda is omega 1 z plus omega 2 z is a lattice. So everything what I said above is true for it. And then you can look at this lattice lambda prime, right? Which is just z plus omega 1 over omega 2 times z. And both these lattices are going to give you elliptic curves. You just go modulo the lattices, you get two elliptic curves, and they are isomorphic because you can go from one lattice to another by just multiplying by omega 2 inverse. So then, sorry. C modulo lambda is isomorphic to C modulo lambda prime under the map induced by multiplication by omega 2 inverse. Okay, and this is very easy to see because you multiply by omega 2 inverse, it's an isomorphism on C, and it will take lattice lambda to lambda prime. So when you go to lambda prime, you look at its pre-image, it's exactly lambda. Okay, but what is it telling us? So this means that every elliptic curve over C gives us an element of H. Okay, using this sort of this method, you take an elliptic curve, then you have omega 1, omega 2, such that omega 1 over omega 2 is in upper half plane, and you can map your elliptic curve to that element of the upper half plane. So this way it is giving us an element of the upper half plane. And maybe I shouldn't be, sorry, I think I jumped a bit. Let me go back a bit and say precisely what I'm going to want to say, and then I can come back to this sentence. But this was not exactly what I had in my mind. I just realized that I jumped one line. So let me just go back a bit. So what we know is that if Z is in H, then we have an elliptic curve associated to it, which is given by Ez, which is just C modulo the lattice generated by 1 comma Z. For everything in upper half plane, you take the lattice generated by 1 and Z, you go modulo that lattice, and you have this Ez, right? So we have an elliptic curve attached to every point in the upper half plane, and from above, we know that if E is an elliptic curve over C, then there exists a Z in upper half plane such that E is isomorphic to Ez or Ez. Right, so this is what we just figured out above when we just multiplied by omega 2 inverse. So every point in the upper half plane, it is giving you an elliptic curve, and every elliptic curve is isomorphic to such an elliptic curve which is given by a point in the upper half plane. Okay, and now if Ez is isomorphic to Ez prime, maybe I should not say if, then this happens if and only if there exists an M in C star. This is an easy exercise to verify that this equivalence is indeed true. There is an M in C star such that when you take M times the lattice generated by 1 and Z, this is same as the lattice generated by 1 and Z prime. So in other words, this is same as if and only if there exists an M in C star, A, B, C, D in SL to Z. I am running out of space here. Z. Such that AMZ plus BM is Z prime, and CMZ plus DM is 1. Because you want the two lattices to be the same. You want the lattice generated by M and MZ to be the same as lattice generated by 1 and Z prime. So therefore, there has to be an SL2Z, which takes one set of generator to the others. And this happens if and only if, of course, Z prime is AZ plus B upon CZ plus D. So you see, what we have proven so far is that two such elliptic curves, they are isomorphic if and only if the Z and Z prime, they lie in the same orbit under the action of SL2Z. Right. So the moral of the story, so conclusion, an isomorphism class of the elliptic curves over C corresponds to a unique point on Y of 1, which is H modulo SL2Z, and vice versa. So in other words, this Y of 1, it is sort of interpolating all isomorphism classes of elliptic curves. You give a point on Y of 1, it is giving you an isomorphism class of elliptic curves over C, and vice versa. You give me an isomorphism class of elliptic curves over C, I'll give you a point on Y of 1 to which it corresponds. So in other words, this means that Y of 1 is the moduli space theorem. So Y of 1 is the moduli space, of isomorphism classes of complex elliptic curves. Okay. All right. Now, obviously, this was for Y of 1. This was sort of an easy exercise. And as I promised, something can be said about other congruent subgroups as well, specifically gamma of n, gamma naught of n, and gamma 1 of n. So let me write down the theorem for you. I won't prove it because anyways, I'm a bit short on time, and once you have seen this proof, and once I tell you what kind of moduli problem it represents, you can just write it down. Once you know what you want to prove, it's very easy calculation, especially with the calculation I just showed. So let n be a positive integer. Then Y naught of n, which is obviously H modulo gamma naught of n. This is the moduli space of equivalence classes so you have this E comma C. I will say what this is elliptic curve over C, and C is a cyclic subgroup of E of order n. Okay, but so Y naught of n is sort of a moduli space which parameterizes equivalence classes like this, but I should give you what equivalence class means. So I should give you the equivalence relation. So EC and E prime C prime are equivalent if and only if there exists an isomorphism between E and E prime, which takes C to C prime. So this kind of so that's what I said. It's a moduli space of elliptic curves with additional data. So for gamma naught of n, the additional data is that you also include a subgroup of order n, and then you take sort of the isomorphism classes or equivalence classes of this tuple E comma C. Whether the equivalence just means there's an isomorphism which takes C to C prime. Okay, so every point of y naught of n, it corresponds to a unique equivalence class of this sort. Okay, so this is like, you can already see the level structure is getting imposed in this additional data. Similarly, for y1 of n, this is the moduli space of equivalence classes. So what are these equivalence classes here? So this is E comma P now, where E is again elliptic curve over C, and P is a point of E, is a point of order n. So if you see in gamma naught, we were considering a subgroup, and now this is a point. And again, equivalence is exactly the same. E comma P is equivalent to E prime comma P prime, if and only if there exists an isomorphism from E to E prime, which takes P to P prime. And part 3 is it for gamma of n.
This P can be called n torsion point also?
Yeah. You can call it n torsion point also. But see, let me tell you, n torsion point means it is killed by n, but not have n order, right? So that's why I wanted to emphasize that it has order n.
Right.
That's why I said order n. You can call it n torsion, but it may have a less order. Like identity is also an n torsion point in a sense. So
how much is the C canonical? Is the C unique?
oh wait, no. C is not unique. So so torsion point is in the first part, right? Here
cyclic group.
Yeah, it's not unique because it's Z mod NZ cross Z mod NZ. So there are n+1, I guess n+1 cyclic subgroups.
Oh, the C itself is Z mod n, right?
Yes, but it is inside E, right? It is inside the
Yeah,
torsion point,
right.
and the n torsion points are not cyclic.
No. So how far C is unique, or what are the moduli for C?
No, any subgroup, any subgroup of order. Okay, I should say cyclic. Any cyclic subgroup. Yeah, sorry, I didn't understand your question.
So if EC is equivalent to E prime C prime,
yes,
then how are C and C prime related?
Yeah, so if and only if there is an isomorphism that takes C to C prime. So C and C prime, n is fixed, right? And C and C prime are two cyclic subgroups of E of order n, and so they are equivalent if and only if there is an isomorphism which takes C to C prime.
Yes. So C is actually contained in some Z mod n cross Z mod n.
Yes.
Yeah, something like that.
Yeah, precisely. It is like a cyclic subgroup of Z mod n cross Z mod n. And finally, for y of n, so this is the moduli space of equivalence classes. So now we have E, and along with E, we have a tuple P comma Q. And the tuple is, so E is again elliptic curve over C, and P comma Q. This is a set of generators of n torsion points of E. Okay, so here we are choosing a generator of En, and again the equivalence is similar, that if we have P comma Q, E comma P comma Q is equivalent to E prime comma P prime comma Q prime, if and only if there exists an isomorphism from E to E prime, which which sends P to P prime and Q to Q prime. Okay, it should send both P to P prime and Q to Q prime. Then only two such tuples are said to be equivalent. Okay, as I said, I'm not going to prove this, but you know what every point corresponds to. So whatever we did last time, we can just do it. First of all, you have to, like, given an elliptic curve with this additional data, you have to find an isomorphism which makes it into this kind of data that we have, with the upper half plane. And then all you have to do is 2 points on the upper half plane. They will give you the same sort of same equivalence class, if and only if they differ by gamma naught or gamma 1 or gamma, depending on the data. So the procedure is really the same. The data is changing, so you have to, like, keep track of that extra thing. But it's not hard. You can also look at Diamond-Schulman for a proof or any other standard introduction to modular curves. But this is like a very important property that we have, that these are moduli spaces. And what happens is that because they have module over Q, you can use them to get moduli spaces of elliptic curves with additional data over arbitrary base. So far we are over complex numbers, but because you have this passage to algebraic curves where they have models over Q, you can use them to get moduli spaces of, like, elliptic curves with this additional data. But now the base field is not Q anymore; it's an arbitrary base. That is a full algebraic geometry theory that comes into picture. And as Professor Kulkarni was telling us that whenever you have torsion inside gamma, this moduli space, when you approach it from algebraic curves aspect, it is not always representable by a scheme. We may have to take a stack or something like that. So it is the kind of thing he was saying. But if n is large enough, then I think you are still in the safe zone. So sorry, this is just an aside. So now we move to modularity theorems. So these are sort of the main goal of my talks from now on, is to introduce various versions of modularity and sort of try to give a relation between them. So very roughly speaking, what modularity theorem says that all rational elliptic curves arise from modular forms. Okay, this is a very sort of the popular version of modularity theorem. Rational elliptic curves mean elliptic curves which are defined over rationals. We have an equation over rationals. So this is very vague, it makes no sense as of now, because modular forms are something which is like complex analytic, and then elliptic curve is algebraic, and it's not even clear what I mean by arise from. To make this slightly more precise, what this means is that you have a rational elliptic curve. You can look at its prime of good reductions and go modulo them, and then you can think of this elliptic curve as a elliptic curve over finite field. I'm hand waving here a bit, and you can look at the number of points of elliptic curve over that. So this is a data, right? For every prime P, you have gotten a number of points of the elliptic curve over FP. And this is interpolated by a modular form of weight 2. This is what this theorem statement says. So maybe that is...
So these numbers appear as a Fourier coefficient of modular.
Exactly. Fourier coefficients or Hecke eigenvalues, but I don't think that language has completely introduced. So I don't want to more about it now, but after in my second talk, I'll say more about this. So this means that if E is an elliptic curve, E over Q is an elliptic curve, then there exists a modular form of weight 2, interpolating the data of number of points of E bar over FP, where P has good reduction, something like this. I'm being very vague here, it's not as if this is not like the very precise thing, but roughly speaking, this is what I mean. Sorry, E has good reduction at P. That's what I should write here.
If something does not have good reduction, there is no scope.
If something does not have good reduction, that means the modulo p you're not getting an elliptic curve. So this is sort of these are the primes which divide the conductor, or in modular form language, these are the primes that divide the level. And we usually, all the Heike operators and all that is mostly away from level. I mean, of course, we have something at the level, but this number of points of E bar or FP, this does not make sense because E is not an elliptic curve anymore.
Why did you put bar on E?
Bar is because of the reduction. E is over Q, right? And this bar, it sort of represents the reduction modulo P. I'm not being precise, so I just kept it at that. So basically, you choose an equation over Z, or at least try to choose an equation whose denominators are not divisible by P, and then you can just reduce it modulo P. That's all. So this is like sort of the main, sort of the more popular statement. But what we'll do is we'll see various versions, because all of this can be said in many different ways, and we'll try to see how they are related to each other. Of course, the proof is out of scope. It's very complicated. So just and history is that. So this was proved by
this P is how many P's you need? P is a prime or what?
P is a prime, and they are all but finitely many.
All but finitely many.
Yes.
So E has good reduction
at all but finitely many primes.
So there are elliptic curves which do not have good reduction.
Yes. So given an elliptic, sorry.
So there are elliptic curves which do not have good reductions at all but finitely many.
No. So elliptic curves will always have good reductions at all but finitely many.
Yes. So there are infinitely many P's with this property.
Yes.
So this is the interpolating data.
No, the interpolating data is number of primes. I see your confusion. Let me just try to modify it a bit.
Yeah.
Data is the number of primes of E bar over FP.
So when you reduce the equation has some only finitely many points.
Yeah.
AP in general terms.
Right. Sorry, I think I used a bad notation, which must have caused confusion.
So these are the number of points.
Yeah, precisely. Number of points of E bar over FP. Sorry, I think I used the wrong notation. But I hope this is clear now. Continuing, what I was saying was that this was basically the famous Taniyama-Shimura conjecture, and it was proved by Wiles and Taylor-Wiles, in many cases, while proving Fermat's theorem. And the final sort of nail in the coffin, you can say, was given by Breuil, Conrad, Diamond, and Taylor. So they proved this in complete generality, and many cases were already proved by Wiles and Taylor. Okay, so now what we'll do is we'll keep on stating various versions of this modularity theorem. So the first version, so I am following Diamond-Schulman here. So the notation will also be very similar to what Diamond-Schulman gives. So the first version of this modularity theorem, this is version XC. It will be clear why it means, why it is denoted this way. So let E be a complex elliptic curve with rational J invariant. Then the modularity theorem says that for some integer greater than 0, n greater than 0, there exists a surjective holomorphic function of compact Riemann surfaces, so this Fe from x naught of n to E. So basically there is a surjective map from x naught of n to E for some n greater than 0. This is sort of a Riemann surface or complex analytic version of the modularity theorem, and the function Fe in the theorem above is called a modular parametrization of E. Okay, so basically it states that for some n, we have a surjective map, holomorphic, from x naught of n to E, given an elliptic curve with rational J invariant. Okay, so this is like sort of the first version of modularity theorem that we know. There is another version which involves Jacobians. So let me very quickly state what that is. Jacobians. So you let gamma, so sorry, maybe some notation here. I'll probably just begin on next page. Sorry about this. Yeah, so Jacobians. You let gamma 1 of gamma 1 whole x naught of n. This is the space of holomorphic differentials. Sorry. Space of holomorphic differentials on x naught of n. So you'll see later on a connection of modular forms with this space. You'll probably see in some other talks, or if you don't see, maybe in Mihir Seichler-Schindler talk, you'll already see this. What key is that if x naught of n has genus n, sorry, genus G, then the dimension, the complex dimension of this space is G. Okay. All right. Now, we let H1 of x naught of n comma z be the first homology group. Of x naught of n. And then we define the Jacobian. So this is a very, I'm just specializing everything for x naught of n, but there's nothing special about x naught of n. This can be done for any Riemann surface. The Jacobian of x naught of n is denoted by Jac x naught of n or J naught of n. We mostly call it J naught of n. Is the quotient group. Sorry. Which is given by J naught of n is the, sorry, I should leave some space. So J naught of n is the dual of holomorphic differentials modulo the first homology group. Okay. So this is the definition, and in fact, this is not just a group; it's an abelian variety. So note that J naught of n is an abelian variety. So C points are given by this. It is again, it's some copies of C modulo.
Instead of taking the dual, if you divide by cohomology group, is that the same thing?
I'm taking dual and dividing by homology group.
Yeah.
Yeah.
Instead of taking the dual.
Yeah. Oh, I see your question. Good question. I am not sure if you, instead of taking the dual, if you can just divide by cohomology group or not. I am not sure about that.
Yeah, okay.
Yeah, I did not think about this, but it's a good question. I don't know. So just continuing. So J0 of n is an abelian variety. And you can also have this modularity theorem in terms of this J0 as well. So let me state that here. There is a bit of things that I would like to say about J0, but I'm not going to say it now because I don't think I have enough time. But let me just say a version of this modularity theorem version JC. It is because now it is now formulated in terms of this J0. Okay, so let E be a complex elliptic curve. With rational J invariant. Then for some positive integer n, there exists a surjective homomorphism. So because J0 of n is also an abelian variety and E is elliptic curve, so again abelian variety. So it makes sense of talking about homomorphism because they let me just finish the statement that there exists a surjective holomorphic homomorphism from J0 of n to E. X0 of n is just a curve, right? We don't know whether it's an elliptic curve or not, and we know examples where it is not an elliptic curve. There are examples where it is an elliptic curve. So in general, whenever we talk about a map from X0 of n to E, there is no sort of what you can say. There is no notion of group homomorphism a priori. But once we pass to Jacobian is an abelian variety. So we can talk about the homomorphism between J0 of n and E. And the modularity theorem, this version of modularity theorem states that if you have a complex elliptic curve with rational J invariant, then for some positive integer n, there is a surjective homomorphism between J0 of n and E. So this is sort of the Jacobian version, and this is same as the version I said previously, which was in terms of X0 of n. I don't have enough time to sort of give the proof now. In the next lecture, I'll try to include the proofs and other versions of modularity. One thing I would like to sort of say about Jacobians before I stop is that if X is an elliptic curve, then Jacobian of X is isomorphic to X. You're not getting anything new. So when you are X0 of n, it's an elliptic curve. For example, n is equal to 11. X0 of 11 is a famous elliptic curve. Then this version is just telling you that there is a surjective holomorphic homomorphism from X0 of 11 to E. So very similar to the previous version. We just said there is a surjective map. Another thing I would like to tell you is that even though the Jacobian I have defined, it is over complex, it is for Riemann surfaces or varieties or complex numbers. This is a much more general notion. You can define Jacobian for any variety over an arbitrary field. But for that, we need to take help of Abel's theorem. So Abel's theorem, what it does, it shows that this J0 of n or Jacobian is isomorphic to the Picard group, pic 0. And pic 0 is something that can be defined for an arbitrary field, for a variety or an arbitrary field. So we take that as the definition of Jacobian, and then the Jacobian can be defined for any variety, any curve over an arbitrary field, rather than sticking to the complex numbers. And when you specialize to the complex numbers, thanks to this Abel's theorem, we get back this formulation that I just showed. Okay, so you may feel that Jacobian is something special, but it is not. Once you know the Abel's theorem, which unfortunately I have like only 2 minutes, so I don't have I don't think I can state it. Maybe I can. Maybe let me try. Abel's theorem says that that J naught of n is isomorphic to pick 0 of x naught of n. And I have not defined what pick 0 is, so let me quickly define what pick 0 is. So pick 0, so it's going to be like a nested definition. So div 0 modulo div L x naught of n. Div 0, these are all the degree 0 divisors on x naught of n. So this is like some nxx, where x is an x naught of n. Such that nx is 0 for all but finitely many x. And summation of the coefficients, it is 0. So these are the degree 0 divisors, and div L, these are the divisors of functions, holomorphic functions. So these are all delta in div 0, x0 of n, such that delta is the divisor for some f inside, so it's a non-zero function on x naught of n, non-zero holomorphic, so it's in the quotient field, a non-zero element of the quotient field of holomorphic functions on x naught of n. Okay, so this is an alternate description of Jacobian, and because this pick 0, all of this can be made sense in terms of algebraic geometry. You can define this pick 0 for any curve, and then your Jacobian is also ready for any curve. So in other words, your x naught of n is over q, right? It's an algebraic curve over q that we saw. So then j naught of n will also becomes an algebraic curve over q because of this alternate route that we can take. So the reason for telling all of this is that there are algebraic versions of the modularity theorems as well. I gave you the complex analytic versions, and then there are the algebraic versions, which tells us that there is a map of algebraic curves over Q from x naught of n to E, and similarly from the Jacobian to E. So what we'll do in my next talk is I'll talk a bit more about all these other versions, maybe give some more details about Jacobian if needed, and we'll try to prove how all of them are equivalent. Okay, because these are just various formulations, but it would be nice to see how all of them are going to be equivalent. So I'm running out of time, so I'd like to stop here. Thank you.
This is what is the start? This is it's a meromorphic function, is that?
Yeah, meromorphic. Yes. So you take the function field of holomorphic functions, so it becomes meromorphic. And star means it is non-zero.
Non-zero or non-constant?
Maybe non-constant. Yes, I guess I should say non-constant, because for a constant function it's just the zero divisor, right? So non-constant.
The divisor would be not finite.
Yeah.
I see. Yeah. Okay. But divisor, to make sense, it has to be genuine meromorphic function.
Precisely.
So thanks a lot, Shaunak, for the wonderful talk. So are there any other questions? Yeah, Professor Kulkarni, go ahead. Okay. So
then, this when you take this quotient, you go back.
So
how is H1, H lower one contained in this dual?
Yeah. So that is based on integral. Maybe try to very informally. I can try to show. This is something I had sort of prepared but I didn't know how much time it will take. So let's say your x naught of n, it looks something like this. And the genus is G, so we have like G holes in a sense. So you have like G holes. And so what you can do is your first homology group, you can sort of take a circle around your hole, something like this. So this is, you call it AI, And then you have, so this is around, and then you can take one vertically also, right? Something like this, just like you do it in torus. You have a horizontal and a vertical kind of thing, BI. And when you look at this, what you can say, so this, you can think of all of these will give you a map from, so how do I say, okay, so we have this map integral around AI from gamma 1 to C, which sends like a differential form is sent to the integral of gamma 1 over AI, and similarly over BI. So this AI and BI, they are sort of the basis of H1, and then you can identify them inside the dual by just get the integration map. So this is sort of a so this integration map sort of identifies this H1 with the subspace of gamma 1.
Okay.
Just integrating forms along with these elements of H1. That's how we get the quotient. So it's a very informally I'm saying. I think Farkas and Kra has a detailed treatment of this Jacobian and construction and everything.
So if these different versions are proved equivalent in the book, all?
Yes, more or less all these different versions, they have been proved to be equivalent in the book. Maybe one or two proofs are left aside because they are maybe more complicated.
In the sense ki how come this complex analytic version that you first gave,
Yeah,
and it would be equivalent to that main modularity theorem proved by VCDT?
it is equivalent. So for that, you need to sort of identify this Jacobian in terms of modular forms. To every modular form, you can associate an abelian variety. That would happen. That would come from the fact that this gamma 1 that is related to weight 2 modular forms. So eventually, all of this will be connected once Eichler, Shimura, and all other things. But if I understand correctly, I think Diamond-Schurman proved more or less all the equivalences.
Yeah, but somewhere they skip something. I have seen.
They do skip something, by the way. They promise you that they will prove, but at some point they say this is out of the scope of the book, or look at
that statement I have read out of the scope of the book.
Yeah.
So, Shaunak, in general, would you like to, maybe there are some young students, some general references for books and maybe some notes by Conrad or something, you'd like to suggest something? Sure.
So actually the literature on modularity theorem is specifically, if you're focusing on modularity theorem, there is not a lot of literature. So Diamond-Schurman is the best book because it is supposed to be for beginners. They don't assume a lot of things. Other than that, for advanced people, there is always Diamond-M, which is more geometric. It is the article by Diamond-M on modular curves. It gives.
Which book you mentioned?
It's an article by Diamond and Im.
Okay.
It's in some Fermat's last theorem proceedings. Another good introduction to modular curves could be David Rohrlich's article in the Fermat's last theorem conference that happened in Boston University back in '95. That is again a very good reference. There used to be some notes by Conrad around, but I don't think they are available anymore. I don't think they are offline now. I think so. I have not seen them. But I would say Diamond-Schurman, Diamond-Im, David Rohrlich's articles, these are very good references to begin with.
Any comment and remark on the motivation, how people see this happening, beginning, conjecture?
Why is this expected to be true? Is
TSW, like Taniyama first see that and then?
I think it was I don't know the history well. I think it was a stroke of genius. I mean, they saw some pattern occurring, and I feel like that's how they saw the conjecture. I don't know why this is natural in a sense. You cannot think of a natural way to convince people that, okay, this is a legit conjecture. Because when they formulated, it was like a sort of I would say a stroke of genius. But at the same time, you see in Eichler, Shimura and all those things, there are seeds of this conjecture present. But when they formulated it, it was like, I think, really something amazing. So, unfortunately, I cannot. I was thinking of how to sort of motivate this, saying that, oh, why this should be true or something like that, but I could not think of like a nice explanation. Maybe before my next talk, I'll try to see if I can come up with some heuristics about why this should be true or something like that.
Plavan, go ahead, please.
Yeah, I want to ask a general question. We are considering for modular curve, we are considering isomorphism classes. But if we consider isogeny class, is there some structure means people study?
Oh, you mean the modular space for isogeny class?
Yeah, means it won't be any structure we have in geometric sense. But
I haven't seen it anywhere. See, the first thing is that whenever you consider modular space of something, it should be representable. That is one of the key things key things that's an important aspect. So I don't know if you just take isogeny classes. I'm not even sure if it is expected to be representable or not. I'm not sure. Maybe something is done. It's just that I have not seen it.
Okay. No, I am asking in the sense of means if you take means arithmetic representation and take the row bar, means the class of that actually. All the representations row having the row bar is fixed. So that class.
Yeah, for that, yeah, you can use modular curves for that. Oh, if you're that specific, then yes.
Okay.
Always take upper half plane modulo. See, if you want to sort of classify all the representations, you sort of take classes with a fixed residual representations. I think do it via modular curve. You have to just choose your gamma smartly.
Okay.
So you see there are many papers on these things. They use it regularly. You just go to any elliptical paper, which is dealing with this image representations and so images of representations and so on, and you should be able to find it.
Okay. Thank you.
So, are there other questions?
The only modular forms are of weight 2, you said?
No. When you go to gamma 1, the dual of gamma 1 is related to modular forms of weight 2. In general, modular forms can be of arbitrary weight.
No, but in this picture, only weight 2 modular forms come?
Yes. In this picture, whenever you're relating with elliptic curves and with modular forms, only the weight 2 ones come into the picture.
So that means what? That at the cusp, they vanish like squares or what?
No, so weight 2 means they are more like differential forms on modular curve rather than powers of differential forms. They are actual
differential forms.
Yeah. So the weight is sort of telling you whether they are actual differential forms or are like powers of differential forms or something like that. So weight 2 means they are actually differential forms.
Yeah, very good.
Thank you. It was nice talk. Yes.
Thank you.
Thanks, Shaunak. Looking for next talk.
Yeah.
Thank you very much. Thank you for the invitation.
Yeah. So thanks a lot, Shaunak, for the wonderful talk. And so, yeah, we end the talk here today.
Thanks to you, Somna, also for coming.
Right. No, it's my pleasure. Thank you, everyone. So,
Luca, can we stop the live stream?
Yeah, I do.